And share the screen. Bring a whiteboard. All right, and let's bring up web work. And we're eventually going to run out of web work problems, so at that point, I think we can continue. But it turns out we're doing pretty good on the schedule. Seems like we're right on course. So I think the last one we looked at was problem. I've got 33% correct on problem 7. So I'm assuming I just answered the last part. And anyway, solve the initial value problem. A good start. Y prime plus y equals t. 0 equals 0. And f of t equals 1, 0 to 1, minus 1 from then on. Okay. And I'm guessing we want to try to use the well, let's see. Can we do this without the Laplace transform? Oh, that seems like it would be pretty difficult. Yeah, let's continue doing this with the Laplace transform like we were before. Don't think it would maximize this. Okay.
Sorry, my cat is crawling all over me. I missed what you said.
Oh, nothing. Nothing important. I was just thinking like we could solve this problem without using the Laplace transform, but I figured
Oh, okay.
It's the Laplace transform homework. Let's just go for it.
Okay, I just wanted to make sure you hadn't like asked me something.
Oh no. Okay, so what do we have? Laplace transform on the left hand side is sy minus 0 plus y equals, and then we want the Laplace transform of f of t. So this is going to be equal to 1 plus let's see, how should I phrase this? So when we take the Laplace transform, let's just go with this. So it's this minus 2 u1 of t. Yeah, so since we're only going to be, the Laplace transform only cares about what happens from 0 onward, so we're just going to write it like this. We could say that this thing, we could write it like u0 of t minus 2 u1 of t, but we would end up getting the same thing. So let's just say 1. And so the Laplace transform of f, which I'll call capital F, is equal to 1 over s. And then we want minus 2 times u1 of t. So I'm just going to double check with my table of Laplace transforms. No harm in doing this. Make sure I don't mess it up. But I think we should have just e to the minus to the minus. Yeah. Right. So that's S, not a 2. Okay, so let's plug this in. 1 over S minus 2 to the minus S. And this is equal to y times 1 plus S. So we divide both sides by 1 plus S. Y equals 1 over S times 1 plus S minus 2 e to the minus S 1 over 1 plus S. Actually, I'm going to write S plus 1. Let's take it. Okay, so now we need to get the inverse Laplace transform. So I'll write it like that. Y of t, our solution. And so 1 over S times S plus 1. Now I think we can just do this. I don't want to do this. Let's do it using partial fraction. So this is S plus 1 equals A over S plus B over S plus 1. I was debating in my head whether I wanted to do this as a partial fraction decomposition, or we could use the convolution for this. So actually, let's just write that out, see what that would give us. So this is 1 over S times 1 over S plus 1, and we know what the Laplace transforms to those are. So we have 1, and then that's involved with what we get for 1 over S plus 1, which should be e to the t. Double check that. E to the negative. So we would have the convolution there, and then this part is a little bit easier. So that would be bring it up on the table. So this is, I'll go ahead and write minus 2 times. So we have 1 over S shifted backwards by 1. And we have a negative 1 in the exponent here. So we can just write this as U. We want to write. Like this. So the inverse Laplace transform of 1 over S plus 1 is equal to e to the, checking, e to the minus t. And e to the minus s. Think about this. Well, let's just do this one as a convolution also. So e to the minus s is hmm, yeah, let's not do it. Let's not do it as a convolution. Let's just do it that order. So this is the Laplace transform, the inverse Laplace transform 1 over s plus 1. And if we have e to the minus s times that, then that's the Laplace transform of u1 t e to the minus t shifted by 1. So e to the minus t minus 1. And separately, 1 convolved with e to the minus t. So that will be integral from 0 to t of 1 times e to the minus tau d tau, which is just the just really the antiderivative of e to the minus t. So we get e to the negative e to the minus tau, 0 and t. So we get 1 minus e. Okay. So unless I've made a mistake in that integral there, that's what we should get for that first part of the convolution. And then we've got the second part already done. So this should be the answer. Now I'm going to check this against partial fraction decomposition to see what I get. So from that, different color, I have 1 equals a times s plus 1. I'll just pause for a second and is there anything that you feel like I've done incorrectly in this problem so far? Okay. It's totally possible that I have. So let's try this out. A plus b equals 0. And then, well, a equals 1, so b equals negative 1. So what we get is that this is equal to 1 over s minus 1 over s plus 1. And, oh, lo and behold, we take the inverse Laplace transform of this, we get 1 minus e to the minus t. So we did the convolution correctly. And we got that part. And then this part, we just did the ordinary. All right. So, well, I'll put that into my work and see if. So 1 minus exponential of negative t minus 2 h of t minus 1 the exponential negative Incorrect. Let's see, what did minus exponential t minus 2 times u1 of t times minus t minus 1. So clearly I've done something wrong. Just double check. So this should be the correct Laplace transform of the left-hand side. And the right-hand side, yes, we did. I think we got the wrong Laplace transform. Right. So this, well, maybe not. Yeah. So this should be minus 2 e to the minus s over s. So I wanted the e to the minus s for the shifting part, but I forgot about multiplying by the Laplace transform too, which is 2 over s. It's not just 2. So what do we get here?
Why is it 2 over s? Like, why do you have to multiply by that then?
The Laplace transform of 1 is 1 over s. It's not just 1. So this is,
okay.
that's the Laplace transform of 1. Yeah. So there's this, I'm thinking of this 2 as just a scalar multiple out in front. And this is the function 1 shifted, the constant function 1 shifted forward by 1. So that's the mistake there. And let's see. I think I'll leave the first term. I think we got that right. And the second term will be, let's see, 2 times e to the minus s over s. So this will be 2 e to the minus s over s times s plus 1. And now we have to get the Laplace transform of this thing, the inverse Laplace transform. So let's see, how can I do this? I guess this let me make a little room here. So 2 e to the minus s over s times s plus 1. This is really just 2 e to the s times, we already figured out what the partial fraction decomposition of 1 over s times s plus 1 is. 1 over s, 1 over s plus 1. And so when we do the inverse Laplace transform of this thing, what we can do is just say that this is the shifted version of the inverse Laplace transform of each of these. So this is the 2 times e to the minus s means I'm going to be shifting forward by 1. This will be u1 of t. Notice the whole thing is going to be shifted forward by 1. So u1 of t times 1 minus e to the minus t minus 1 will be shifting that part forward by 1. Of course, the 1 is already, you don't need to shift that forward. So then what I should get here is minus 2 times, writing it in the notation that Webwork likes. 1 minus the minus. And minus t minus 1. Answer correct. Okay. Yep, that was the problem. Okay. So let's go any further. Okay, next problem. Problem 9. The valuable lesson to be learned: never get discouraged. What? Okay, that's not something that's just not rendering. It's solve the initial value problems of the differential equation by Laplace transform. Please give the coefficients of any exponential functions as fractions along with any constant. Okay, so this must be like a making sure it's formatted so that Webwork doesn't get confused. Anyway, what do we have? Y double prime minus 6y prime equals e to the 5t. Y of 0 equals 0. Y prime of 0 equals 0. So that'll make the Laplace transform easy to do. It'll be s squared capital Y minus 6s capital Y, yep, equals, and then e to the 5t, which should be 1 over s to the minus 5, I think. Look. 1 over s minus 5, and 1 over s to the minus. That doesn't make sense. Okay. Now y times s squared minus 6s equals 1 over, make my s's and 5s a little more clear so they don't look like the same thing. And y equals 1 over s minus 5 times s squared minus 6s. Now, I'm guessing that this is something that they want us to solve using partial fraction decomposition. Okay, so let's do that. This might be an interesting situation in which we can do the convolution. Let's give it a shot. I might be getting myself into a lot more work than I actually want, but we'll see what happens. S minus 6. So this is just 1 over s times 1 over s minus 5 times 1 over s minus 6. And so y of t will just be 1 involved with e to the 5t involved with e to the 6t. And this expression makes sense because what we said about the convolution is associative. So we can do these in the order we want. So what do we have? We have 1 convolved with e to the 5t is integral from 0 to t of 1 evaluated at t minus tau, so that's 1, times e to the 5 tau, e tau. And so this works out just like before. This is 1/5 e to the 5 tau evaluated at 0 and tau. So this is 1/5 e to the 5t minus 1. I'll just write it as, yeah, 1/5 e to the 5t minus 1/5. Right. So this is 1/5. It's probably better like this. Probably better the first way I wrote it. E to the 5 t 1 involved with e to the 6. This is, I guess, good practice because we'll get to see some of the properties of the convolution. One of them is that I can pull this 1/5 out, and the other, it's a linear operator. So, or it's a bilinear operator. It's linear in both sides. So I can pull the 1/5 out, and I can write it as e5t involved with e6t minus 1 involved with e6t. So what are these? 0t, e, now we have something that we can work with, e minus tau, e to the 6 tau, et. And so we can combine the exponents together, 0 to t, 5, t minus 5 tau plus 6 tau t equals 0 to t, e to the 5t times e to the tau, tau, and t doesn't depend on tau. So whenever we integrate, I want to be a little careful, but it doesn't depend on tau, so it's just going to be t is some constant with respect to this the tau that's being used in the integral. So this is going to be e to the 5t times e to the tau, the antiderivative of the tau, 0 and t. So I get e to the 5t times e to the t minus 1. So this is e to the 6t minus the 5. What I get is 1/5 e to the 6t minus e to the 5t. And then for the convolution of 1 and 6t, we can see it's going to work out exactly like the convolution of 1 and 5t. It'll just be this thing, except it'll be 6 instead of 5. So 1/6 e to the 6t plus 1/6, because it would be minus minus. Okay. Now, assuming that we've done all this correctly, which is a big assumption, we'll have 1/5. I should say, I've done all this correctly. I'm not putting any of the blame of mistakes on you. 5/6 e to the 6t minus e to the 5t plus 1/6 And so what I should get is 1/6 e to the 6t minus 1/5 e to the 5t plus 1/30th. Now, before I go back and check this with partial fraction decomposition, which I really do want to do, I'm going to go ahead and wait. I don't know if we'll have the same kind of motivation if we find out this is correct to even bother with the partial fraction decomposition, but let's see. 1/6 e to the 6t. I'm just feeling really impatient. Exponent t plus 1/30th. Oh, and that's correct. Oh, that's beautiful. Okay, so the convolution had all worked out. But let's just do the partial fraction decomposition for practice. So what we should get is, or no, let's work from this point here. Can I just grab this? Oh, it didn't take the one. It's worthless. Okay. 1 over it's 1 over s minus s minus s times s minus 5 times s. I don't remember it that long. And since we're changing methods, let's change color. So this should be equal to a over s plus b over s minus 5 plus c over s minus 6 for some values a, b, c. We can just kind of compare the levels of difficulty and decide we have to do something like this in practice, which one we prefer. So that's a, and then b, s minus 6, and then c, s minus 5. And so I'll just go ahead and expand this out. A times s squared minus 11s plus 30. That'd be kind of a pain to do in my head. B times s squared minus s. These two wouldn't have been so bad. S squared minus. So a plus b plus c is 0. Minus 11a minus 6b minus 5c equals 0. And 30a oh, hey, that works. We see the 30 already. 30a equals 1. That's great. Okay, so so a equals 1/30th. And now we've got a couple of equations here to deal with. So we have 1/30th plus b. Let's do it like this. B plus c equals negative 1/30th. And six b plus 5c is equal to negative 11 over 30. Okay, it's a huge pain. Well, so bad. Yeah, what do I want to do with this? I'm just going to do it the kind of the easy way. So minus 5b minus 5c equals 5/30ths. And what I'll get is, I'm going to add those together. B is equal to negative 6/30ths. In other words, negative 1/5. Yep. Okay. So that's A A, B. And it looks like we're on the right track. We should get 1/6 for C. I think. So we have C is equal to 1/5 minus 1/30. So that's 6/30 minus 1/30, which is 5. So we get capital Y is equal to 1/30 1 over S plus 1/5 1 over S minus 5 plus minus 1/6. Hmm? No, 1/6 here. 5/30. So this should be minus, and this should be plus 1 over S minus 6. So this will give us 1/30, or sorry, not equals. So this is the inverse Laplace transform. Y of t is equal to 1/30 minus 1/5 e to the 5 t plus 1/6 6t. Is that what we got before? Yeah. Okay. That's worked out again. Now this looks, I mean, like I've said many times, this looks like a totally different, we've done a totally different thing, and yet, and did a lot of work in the process, still came up with the same answer. I think. Okay, solve the initial value problem, and WebWorks doing its WebWork thing, and saying it's y double prime plus 0y prime plus 1y. You know, WebWork, you could have left out those parts. Equals h of t minus 12, which is the same thing as 12 in the notation of Poisson de Prima. The y of 0 equals 15, which I should write 9, and y prime of 0 equals 0. UnWebworkify that. And what do we get? Well, if we take the Laplace transform, we get s squared capital Y minus, write it as 19s, equals e, and let me double check on my Laplace transform table so that I don't mess it up. So e to the minus 12s over s. Now, time to get to work. So let's see. I will move that 19s over the other side and divide by s squared. What do I get? I won't do it in my e to the minus 12s over s plus 19s, and then y equals e to the minus 12s over s cubed plus 19 over s. So that part will be easy. That'll just be 19. Now this s cubed, what do we have in our Laplace transform table? We know that, okay, we're getting this from the Laplace transform table. T to the n the Laplace transform of this is equal to n factorial over s to the n plus 1. Interesting formula here. Kind of looks like the power rule for integrals in a sense. So if we want the power of s in the denominator to be 3, we're going to choose n to be 2. So this will be Laplace transform of t squared will be 2 factorial, which is 2 s cubed. So I'm going to write this as e to the minus 12s times e to the minus, let's do it like this, 1/2 e to the minus 12s, break out all the parts, times 2 over s cubed plus 19 over s. So what is this equal to? Now, what is it equal to? What is the inverse Laplace? So that will be 1/2 times whatever the Laplace transform, inverse Laplace transform this is. And so we know what the inverse Laplace transform of 2 times s over 3 cubed is t squared. So this will be u12 of t times t squared, but shifted forward by 12. So times t minus 12. Not a 6. Yes. And this is just possible. Now I'm looking at this and I'm thinking, this doesn't seem quite right to me. It starts off at a position 19, and then for 12 units of time, it just stays there. And then at 12, we get this impulse. Well, it's a continuous force of 1 unit. Well, let's see what WebWorks says. We got it right. One half h t minus 12 squared plus 19. Incorrect. This doesn't look right. Doesn't seem like the way a physical system would behave. What did I do wrong? Oh, you see it? The initial step where I did the Laplace transform, I left something out. This is why it's good to have kind of an intuition about how these things. This is supposed to represent a mass on a spring, and it's really hard to imagine that this is actually how a mass on a spring would behave. It just sits there at 19 inches away from the equilibrium. So I'm going to wipe this out and try it. Some of this I could have left, but rewrite it. All right, come on, tablet, catch up. So this is the correct Laplace transform for the y double prime, but I didn't do the Laplace transform for just y. We should have a plus there. What I did, okay, so what I did, I left this term out, just continuing on this theme of the physical intuition. I accidentally left this term out in the Laplace transform. So I did the Laplace transform of a system where the mass has 1, it has a mass of 1, but the spring restoring constant, the spring constant was 0. So there was no spring. So of course, if it's at a position 19, there's no spring to move it, it stays at 19. Okay, so that kind of makes sense. Now, with this y here, you'll see that the equation will change. This was e to the minus 12s over s. And so let's see, what do we get now? S squared plus 1 times y equals e to the minus 12s plus 19s. I think a lot of people who are watching these videos will write the evaluation form. Like he made so many mistakes. I never knew what was going on. But I think it's good to make a mistake like this and then notice how things can go wrong, right? This is a low stakes situation. It's not an exam. Certainly not for me. Okay, so y is equal to e to the minus 12s over s times s squared plus 1. I think really student evaluations are just an opportunity for a little bit of revenge. Just you get to take your frustration out on me for a little while. Okay, so now what do we end up with? This is a little bit harder. Well, let's take that first one. So that first one is e to the minus 12s times 1 over s times s squared plus 1. And now this one is going to be kind of a pain. We'll do it with partial fraction decomposition. Actually, we could do this using convolution again. Well, let's try it. So the 1 over, change to a different color, so 1 over s times 1 over s squared plus 1. The inverse Laplace transform will be 1 involved with, it's kind of easy to do the convolution with 1. It doesn't give you the same thing, but it's like a simple integral. And the s squared plus 1 is just sine of t. So this will be integral from 0 to t of 1 times sine of tau d tau. And so this is equal to negative cosine of tau evaluated at 0 t. And so this is equal to 1 1 minus cosine t. What we should get. Okay. Now let me try this with, I think that worked out pretty easily. That was an easy integral, I think, in my mind, a relatively easy integral to do. Now what happens if we do this with partial fraction decomposition? Does it turn out to be easy? So we have 1 over s times s squared plus 1 equals a over s plus, and now we need a linear bx plus c, s squared plus 1. So this will be 1 equals a s squared plus a plus bx s plus c. Okay, so should be bs squared. It should make sense. What I'm doing should make sense. A plus b equals 0. C equals 0. A equals 1. B equals 1. And so we get 1 over s plus 1 over s squared plus, no, minus s over s squared plus 1. And then we take the inverse Laplace transform of this, and we get 1 minus. I guess that kind of worked out to be maybe the same amount of difference. So I was wrong. It wasn't, it turned out to not be a pain at all. And well, that basically gives us our answer. So I'll switch back to black. Y of t. So we have the inverse Laplace transform of this part right here, and then e to the minus 12t just shifts it. So this is u 12 of t times inverse Laplace transform that we got. So that's 1 minus cosine t. Actually, 1 over s times s squared plus 1 may be one of the things that's in the kind of standard Laplace transform table. Maybe not. Maybe not. Anyway, it's always nice to use the table if you have it. Sometimes it's good to have practice. Anyway, that's our first part. So that's this part. And now this part. That one's easy because we know that s over s squared plus 1 is just cosine. This is plus 19 cosine. So what is this? It starts off with an oscillation. This oscillation has an amplitude of 19. Well, it starts off at 19, and then it swings back and forth from positive to negative 19 with a frequency of 1 hertz, 1 per unit of time. And then at this this point right here, we introduce another kind of vibration to it. Okay, so that seems physically plausible. The spring, we should have an oscillation. So let's see what Webwork thinks. H of t minus 12 times 1 minus sine t plus 19. And that is correct. Okay. So we have successfully done all of the homework and used up almost all of the class time. I'll just really quickly give a brief overview of what we're going to start talking about next, and then we can do that tomorrow. And that is, well, maybe I'll start off with just kind of a motivation. So why are we doing this? So we've been working on this kind of really interesting type of equation. So the second order linear equations, non-homogeneous usually with constant coefficients. And we want to see if we can we extend to non-constant coefficients. So that's just like that's a natural next question. What can we do to do this? And in order to see where we might have problems, we'll look at what we've been doing before. And now setting aside for a moment the Laplace transform method of solving things, we break these things down into 2 steps. One is find a fundamental set of solutions. So these are solutions to the homogeneous equation. And then find a particular solution, and this is for the non-homogeneous equation. Now, all of the methods that we've been looking at for the step 2, they work for any kind of coefficient. We didn't take, there was no assumption that we had that the coefficients were constant. Once we had a particular solution, no matter how we found it, it didn't matter. We could use any kind of method we wanted. We had a particular solution. And all of the solutions, the kind of general solution, varied from that by linear combinations of the fundamental set. And all of the methods that we had for getting a fundamental set involved having constant coefficients. So we could only deal with that situation. We had constant coefficients. In fact, if we wanted to do the Laplace transform with non-constant coefficients, we had a little bit of trouble because we didn't talk about what was the Laplace transform of t squared y double prime, for example. What is the Laplace transform of that? We can figure it out. Involves looking at that integral and doing integration by parts. We could figure that out, but we didn't talk about that. So this is a problem. What can we do when we have non-constant coefficients? And the answer is we start with a new tool, and that tool is series solution. So what we're going to do is assume the solution as a power series representation, and then solve for the coefficients of the power series in a way similar to the method of undetermined coefficients. Now, we might ask ourselves, well, we had that we already had the method of coefficients. That was something that we used for non-homogeneous equations to find a particular solution. Is there a way that we could apply something like that to homogeneous equations? Is there something that we can do there? So an interesting question to think about for the next class is what might go wrong? What would be the problem? Okay. So next time we're going to we'll review power series, and this is chapter 5 in Voice de Prima, but this is when I teach Calc 2, this is one of my sort of favorite topics in the class. I know for students it's usually one of their favorite. But power series are really interesting mathematical objects, and so we'll spend some time reviewing that, and I'll go into a little bit more detail in Voice de Prima to kind of help this make a little more sense. Anyway, I think that's it for today, and I'll see you tomorrow.
Bye. Have a good day.
You too.